Good afternoon, everyone. We're glad to welcome you to our SAP Tech Talks webinar. A few words regarding the event organization. The webinar will be recorded and then posted on our YouTube channel. You may ask all your questions in the Q&A field. Our today's speaker is Jurijs Tolokoncevs, and the topic of his webinar, From Celestial Bodies to Chatbots, Demystifying Neural Networks. I give the floor to our speaker.
Hello, everyone. Very glad to see you in such big numbers. Was not expecting such participation, but let me share my screen. Okay, guys. So our tech talk is called Neural Networks. In a nutshell, demystifying neural networks. I'll introduce myself. I'm Jurijs Tolokoncevs. I'm working as engineering manager in EPAM, and I've been working in the technical IT sphere for about 17 years, and I was interested in neural networks even before that in my university times. So I got very interested in the topic, and I was following it closely ever since, and I thought I can share a little bit of what I learned. So before we go to agenda and everything, I wanted to put a stage. So there are a lot of buzzwords that have been popping up lately, like all ChatGPTs, Midjourney, Copilot, deep learning, neural network, and everything. Like, it's been mentioned everywhere. And sometimes I feel like you can get lost in all of this information unless you have a good foundation, unless you can get some understanding on what it is, and it will help you understand also topics above and everything that's happening in the world right now. So that's what I want to try to do in this presentation. And before we go into our agenda, that will consist of history of neural networks, and then I will be talking about different types of neural networks more closely. I want to mention a couple of interesting stuff. Like, for example, we take a look here. This is a search term, artificial intelligence. And it's from Google Trends, and you can see that searches for artificial intelligence have increased dramatically recently. And there was this small event that kind of paved the way for increased public interest in artificial intelligence. That's happened around December 2022. And just try to think for yourself, what was that? Because it's obviously a spike that then led to increased interest in the whole area. And of course, it's not a very big secret that was the release of ChatGPT. And therefore, I want to try to get from the very basic and get to the point when you understand what ChatGPT is. I think this is the biggest goal for me, because if you go through this journey with me, you will have very little problems understanding the whole artificial intelligence area. So also, before we continue, I wanted to explain some common terminology. Artificial intelligence, this is a very big field. It basically includes everything where machines try to simulate humans, try to simulate human intelligence. It doesn't even have to be computers. Sometimes you can take a look at the book, like Choose Your Own Adventure book. It's also type of artificial intelligence where a book simulates like an author or a dungeon master in a Dungeons and Dragons game. So this is also type of artificial intelligence. But there are more, and one of types of artificial intelligence is machine learning. And machine learning is when machines are learning and they are building their own algorithms without human intervention. So machine learning are a subset of artificial intelligence, but then not every machine learning is a neural network. Neural network is part of machine learning, but it's not every part. There are other stuff like swarm algorithms, and there are genetic algorithms, which are not neural networks, but are still machine learning. So yeah, then there are neural networks. This is the algorithm that simulates the way how neurons are structured in human brain. And those are neural network, and even deeper, if we go into those, we have deep learning. Those are bigger and more complicated neural networks that can encode much more complex ideas because there is much bigger complexity inside of them. And this is where all the interesting stuff happens. At this point, deep neural networks and deep learning is where the frontiers of artificial intelligence are explored at this moment. Like all your DALL-Es, Midjourneys, and ChatGPTs, everything is happening in this area. So let's talk a little bit about history. And I like to start from quite far away. Like imagine in 1795, you're a young guy looking at stars, and you're an 18-year-old mathematician. And you're trying to help your fellow scientists because they have lost a planet. Like there was recently a dwarf planet discovered in the asteroid belt called Ceres. And it was discovered, but then they lost track of it. And he was trying to help them find it again. And what was he doing? He was tracking its position. He was going into history, plotting places where this planet was seen. And he was trying to derive its future position from its past position. And this young guy, like anyone who is interested in mathematics, 100% knows him. He's a very famous mathematical figure. This was Carl Gauss. He was even nicknamed Prince of Mathematics, and he's a big deal in the world of mathematics. He has touched almost everything. Yeah, and by doing this exercise of finding Ceres, he actually developed a whole model of like a new mathematical approach. Not really new, but he really made it mature, which is called linear regression. So anytime you have ever been in Excel and have done that, you've been using mathematical, this linear regression and something that paved a mathematical model to neural networks. But then many years in the future, a couple of guys, neuropsychologist and mathematician, Warren McCulloch and Walter Pitts, they published a paper. They wanted to know how neurons might work. They were modeling them as logic gates. They were modeling them as electric circuits. This was also one of very early times when people try to understand how neurons in the world and in your brain work. And then 1957, another young guy. Also, he was not mathematician, he was not computer scientist, not physician. He was actually a biologist. He was interested in how eyes of a fly work. He wanted to understand the way how it works, and by pursuing this interest of his, he developed the first idea, a mathematical model of a perceptron. Basically, an idea that you can have inputs, you can have weights applied to those inputs, and then you do multiplication and summation on all of them. You apply some function and get the result. And this was quite a breakthrough. And he managed to even build an actual physical machine of his perceptron, which was quite successful. It was able to distinguish between simple images, which was absolutely fascinating at that time. And the interest in this area skyrocketed. And there were, like, everyone was talking about it. It was very, very, very interesting for people and for media and for scientists. And everyone started researching. And there are even old videos from that time. That one of them, very short one, we're going to look today.
In the 1950s and 60s, scientists built a few working perceptrons, as these artificial brains were called.
He's using it to explore the mysterious problem of how the brain learns.
This perceptron is being trained to recognize the difference between males and females. It is something that all of us can do easily, but few of us can explain how. To get a computer to do this would involve working out many complex rules about faces and writing a computer program. But this perceptron was simply given lots and lots of examples, including some with unusual hairstyles.
But when it comes to a beetle, the computer looks at facial features and hair outline and takes longer to learn what it's told by Dr. Taylor. Andrew Cruikshank's wig also causes a little heart-searching.
After training on lots of examples, it's given new faces it has never seen and is able to successfully distinguish male from female. It has learned. While promising, this approach to machine intelligence virtually died out.
Yeah. And that's true. This approach to machine intelligence virtually died out because it was ahead of its time. It required a lot of processing power. It required a lot of data that was not available at that time. No progress, no funding, and kind of scientific community, except few people, lost interest in that. But then the new era came, the era of internet, the era of cloud, the era of big computing powers, the era of big data. And now we see the revival of this field because there is processing power, there is big data, and there is much progress, and therefore a lot of funding. So that's kind of what it is about. And now we're going to talk about artificial neural networks. But we just let's try to understand where are we going to be on this artificial neural network front. First, there was this perceptron, inputs converging in a node and then going to the output. If you extend this node into a hidden layer, this is like a simple neural network. Then you can add hidden layers and it becomes deep neural network, much more complicated. But in order to explain the inner workings, we will be looking at this one. I think the most classical example. But like a small segue before we go, let's talk about matrices. Sorry, wrong one. About those. I wanted to kind of bring your attention to the fact that matrices are just numbers written in rows and columns, and you can perform operations with them. And this is very important to understand how neural networks work. You need to understand that you can add matrices together or subtract them just by subtracting or adding corresponding values in the matrix. And you can also multiply them in a similar way. And this basically is all you need to know for understanding basics of how matrices work and how neural networks structure in the middle, like inside. So let's think of an idea. Let's think of a neural network that we want to train to show how it works. Let's look at the tic-tac-toe game. Let's try to build a model that is able to identify if a certain board of tic-tac-toe is possible to achieve, or not. Certain boards are achievable by playing a normal game of tic-tac-toe. Certain boards are not achievable. And let's try to train a model that's going to do that. First, we need to encode tic-tac-toe boards as numbers. Let's say X is 1, O is -1, empty is 0. We just stretch them into lines, and let's say upper ones are the ones that are invalid, lower ones are the ones that are valid, and then we assign an expected answer to each of them. If the board is invalid, we expect 0. If the board is valid, we expect 1. There are much more possible boards than that. There are thousands. I'm just showing this one as an example. Then we will take some of those and we will use them for training. And we will take remaining ones and we will not be using them for training so that the neural network doesn't see them at all. But we will be using them for evaluating and testing how good the model performs. Yeah, let's take it. And we will be concentrating only on the first row in the beginning. So we build a neural network. Basically, the number of nodes will be the number of input values, 9 in our case, because there are 9 fields on the tic-tac-toe board. We have a hidden layer of a similar size. It doesn't have to be similar size, but I just chose it to be similar for just easier understanding. And then there are weights between them. Basically, each node has a certain weight to a connection to each other node in the hidden layer. And all of those values are random in the beginning. And we can represent them just with numbers and with matrices. All inputs can be represented as the one-dimensional matrix, and all weights can be represented as two-dimensional matrix, and you can perform operations with them. Then there is such a thing as biases. So you don't have to understand too much what it is. It's just a value that you add or subtract from the result in order to nudge the model a little bit towards quicker convergence on the right answer. Because without it, it can take too much and too long for it to actually get the correct result and to be trained correctly. So yeah, and then we have output weights that will be applied before we get the answer. And you just do mathematical operations. You just do the input matrix, times it by input weights, add biases, times them by output matrix, and you get the result. And in this case, it's just 4.9994, like a number that doesn't tell us anything yet. But let's look at it closer. 4.9994 is not really useful to us because we want to get result 1 or 0. We need to know, is it a valid or an invalid combination? So there is such an approach as activation function. In this case, this activation function will be squishing the result and trying to force it to be between 0 and 1. There is a mathematical formula for it, but it doesn't matter that much. Like, all you need to know is that you take an input, apply a mathematical formula to it, and the output will always be between 0 and 1. So yeah, so our input that we provided with random values gave us 0.99, basically, which is not really good because it is our answer, but we expected 0. So it's like pretty much as wrong as you can get. But don't be worried, there is such a thing as backpropagation. And you don't have to understand the mathematics behind it, I will tell you. And like, it can be a little bit daunting looking at this idea. But what backpropagation is taking your end result, comparing it with your expected result, calculating how much is the error, how much wrong you are, and going back and adjusting your weights, basically. You just adjust your initial weights a little bit to get to a new matrix. And after doing this, in our case, about 6,500 times, you get a totally different set of weights that is much more suited for your application. And that actually works much better. And anything that you do inside this neural network, like, the mathematics is quite simple. Like, each step is quite simple. There are a lot of those steps. Like, technically, you could do it in something like Excel, for example, which you would have to be a little bit crazy to do it in Excel. So that's why I've done that, and I want to show you. Yeah, and here we are. Just after some tiny 6,500 iterations, our error went down, and it kind of settled down at its minimum. It's not going down anymore. But then, yeah, the final model was 96% accurate, and it is not ideal. It's not wonderful, but for such a small neural network as ours was, it was quite small. And here is the example how 96% accuracy looks. Like, this is 100 by 100, 10,000 samples, and green ones are correct and red ones are incorrect. So if you are in a hurry and if you really need to go, this is I think we're 90% of understanding of what neural network is has been given to you. I have more, and I will talk about different types of neural networks, but for now, this is like the very core of what neural network is: backpropagation, input, output, and error, and trying to minimize the loss function. Yeah, so as I talked to you, deep neural networks are just bigger neural networks. They can encode much more complexity, and they are much more complex inside, because instead of multiplying like inputs by a matrix, you then multiplying matrix by another matrix, by another matrix, by another matrix, and it just grows exponentially, and it is big, it is computationally intensive, but it also can encode a lot of complexity. And basically everything fun and everything interesting right now is done with deep learning and with deep neural networks, like language processing, self-driving cars, visual recognition. All of this fun stuff is done with deep neural networks. And when you go to a deep neural network, like, there are different architectures. You don't have to know about them. You need to know just that there are very different architectures, and while you have those, you can build them, you can do some decisions, you can implement different types of nodes, and there are endless variants that can happen inside a deep neural network. So let's talk about one of them. Let's talk about one special application of a deep neural network, which is a convolutional neural network, which is basically meant for and used for computer vision. So let's say we have a task. We need to recognize a number. We need to recognize a number which was handwritten, and we need to classify it. Like, for example, here we have 28 by 28 pixels, and there is a number 7 written here. How do we even approach this? How do we approach trying to classify this number? First, well, can we use a neural network? Can we use a neural network that uses each pixel as an input? So you have 28 by 28, 784 nodes, 784 hidden layers, then 10 outputs, and we just train neural network as previously. It could work in this case, but it's like over 6 million weights. It is huge, and we are not dealing with huge numbers. We are dealing with just a number 28 by 28 pixels, which is not impressive. What if we had to deal with an HD image? And what if we had to deal with 4 hidden layers instead of 1? HD image with 4 hidden layers instead of 1, which you wanted to build in such a way, would take more, and you just use 1 bit for each weight, for each connection. It would take 10 million times more storage than world has at this moment. Like, it's absolutely bonkers, and it's absolutely impossible to use it in such a way. So what else can we do? Like, many of us are software developers, we are inventive. Let's think of other solutions. What if instead of pixels, what if we start to try thinking about features, like a vertical line, horizontal line, crossing? And let's try to build neural network with those in mind. It could work, but then a feature is a very vague term. Like here, yeah, you see number 7, but like even this is a number 7, and there are totally different features. How do you define it? How do you rigorously define what a feature is to be able to use this approach? And the answer is yes, you can, and I'll show you how. There is such a thing as a filter, which is used in those convolutional neural networks. And yeah, filter is, as famously said, just a matrix, just some values written in a grid. And you can apply this filter to a portion of a screen. You can apply it to a portion of a screen and get some kind of result. In this case, the result is 0 because nothing overlaps. And if you multiply it by each other, you get 0. Like, it's either 1 by 0 or 0 by 1. And when you sum everything together, it's just 0. But you can apply different filters to different parts of the screen. And you can get different values. If there is more overlap, the value will be bigger. If there is less overlap, the value will be smaller. So we have this horizontal filter, vertical filter, diagonal filter, and they all produce same results. Of course, the bias is used here as well. You just shift everything to the left, so that 0 becomes -9, 10 becomes 1, 11 becomes 2. But eventually you just take normal mathematical operations on those two matrices, and you apply an activation function. In our case, an activation function is not a sigmoid as we used before, that if you remember was squishing value between 0 and 1, but this one just removes zeros. Basically, everything which is negative, it ignores. Everything that is positive remains. And you take this filter that we have here, and you apply it to the whole image, step by step by step by step, to each area of an image like this. And you get the end result. You get the end result, which is an image with a filter applied. Here, for example, this horizontal filter is detecting horizontal lines in the image. You can have different. You have diagonal filter that detects diagonal lines, vertical filter that detects vertical lines, and those are your features. Like, this is a rigorous mathematical way to define what a feature is. This solves the problem that features are subjective. And also, if you notice that the resulting image is 24 by 24 and not 28 by 28 as the initial one, because every time you apply a filter, you are reducing the image basically by the size of a filter, because it can go beyond the edges. So yeah, that's how it goes. And then instead of working with individual pixel, you work with those filters. You apply a filter, then you pass it forward, you apply a different filter, you pass it forward, apply a different filter, and every time it shrinks, and you can use backpropagation in the same way to change the filter a little bit. So and then when the image shrinks enough, you can just unwrap it, and if you see like this big layer in the middle, you just unwrap it, and then you proceed with it as a normal neural network, where, let's say, if you pass this to the network, you get number 7. It's pretty sure it is number 7. Yeah, you just use this approach, and that's how most of vision works in artificial intelligence. But this is like an example how in real life the filter may look. It will not be something you recognize. After you've trained the model, it will not be like vertical lines, diagonal lines. It will probably be something absolutely alien to you, but it's what works best. Yes, and this is about convolutional neural networks and how vision works. But now we get to the fun stuff. Let's talk about recurring neural networks. And when we talk about recurring neural networks, let's say we have a task. Predict the next word. Michael was very surprised to hear Vicky said she did not see him at the party. He clearly remembered her talking to, and we need to predict the next word. So the question, can we use simple neural network here? Let's think about it. And spoiler, answer is no. But why? First of all, the order matters. And in neural network, order doesn't matter. But here, somehow, we need to make sure that Michael was very and very Michael was are not the same, because it is important for language processing. And second, we don't know how many words are in a sentence. And before, like, we always had to know exactly what is the size of input in our neural network. So yeah, like what do we do? And the answer is recurring neural network. For me to understand what it is, let's simplify our network a little bit. We have our input, we have our hidden layer, we have our output, but it would be very hard if we worked with the whole network. Let's just simplify it like that. Output, middle, input. And the idea is to take neural network and to start feeding it into itself. Just feeding neural network into itself, the same neural network. You are always using same weights, you are always using the same architecture, and just feeding it into itself, getting some output, feeding it into itself with some additional input, but you're always reusing the same neural network. And there are some weights that will be for the output, for the input, and for this feed-forward mechanism. But the network is itself the same. For understanding it easier, sometimes people unwrap it, so you see what is going on. But technically, it is the same. Like Like those are different time steps, and each time step you are feeding network into itself. Weights, same weights. Yeah, like for example, you can feed Michael, and then you can feed was, and then you will get result like vary. And this is like a normal propagation through time. But if you get like something that is wrong, that is big, you calculate the error and you do back propagation, and in all others you just adjust those weights a little bit, which sounds fun and good, but there are some problems with this approach. Let's say we look at this sentence. Michael was very surprised, blah, blah, blah. He clearly remembered her talking to him. Like the word we need to predict is him. But him is relying on the word Michael. And the word Michael was so far away. It was 22 iterations away. And by the time you have done 22 iterations, the connection between those two is very weak. It is very weak and almost non-existent. And this thing is usually called vanishing gradient, which was a big problem with recursive neural networks. It basically means if you take a weight, and because the neural network is always the same, you're always taking the same weight, and you reapply it to yourself many, many, many times. If it is smaller than 0, it just vanishes into nothingness. But if it is bigger than 0, it just explodes to infinity after like 100 iterations. So vanishing gradient, exploding gradient, those were quite significant problems. And it just meant that like those recursive neural network had memory, but it was a short one. Like you had no chance of neural network making decision based on the word that was like 100 words away or 1,000 words away. And yeah, so a lot of applications were thought of for those. Like for example, if you take one input and gather multiple outputs from this input, you have something like music generation, image description. When you do it differently, when you have multiple inputs but only one output, you could do sentiment analysis, text classification. Or you can even have multiple inputs and multiple outputs, and there you have like machine translation. Like all of this was used, but yeah, it wasn't very, because of vanishing gradient, it wasn't very popular, and it wasn't very powerful. But I think I wasn't very honest with you, and I wasn't very fair, because many of you now may have a question. Yeah, we can put numbers into a neural network, but what do we do with a word? How do you feed the word into a neural network? Like that doesn't work. So a small segue, I will show you a trick how this is done. And if you have worked with any like large language models, there is a word token, and that's where it comes from. It's tokenization. So basically, you take the whole dictionary of words that neural network knows, and you rank them from 1 to whatever. You rank them one by one in alphabetical order, for example, and you give each number like a sequential number. Each word you give a number. And this is basically a vocabulary of your recursive neural network. And then you represent each word as a vector where everything is a 0, the vector of the size of your vocabulary, where everything is a 0 except one place where there is 1, and this place is the sequential number of your word. So like Michael would be this, Barry would be this, was would be this. And because everything is 0 and only 1 is 1, it is called one-hot representation. So I just thought it was interesting fact. Yeah, but then we talked about vanishing and exploding gradient. Let's talk about evolution of recursive neural networks. Initially, it was solving some problems. It was handling sequences, like in a sentence. It has some short memory, but it had exploding and vanishing gradient. It wasn't ideal. Then people were exploring. People were kind of testing and playing with different algorithms. And there was a next evolution of this recursive neural network, which was called long short-term memory. LSTM. And I will not be going deep into how it worked inside because it would be too long. But what you need to know is that basically there was a new algorithm applied, and there were different decisions to be made. There were some gates applied to recursive neural network that could decide whether to remember or forget some information. And that basically introduced a long-term memory to recursive neural network, and that's when it could handle much bigger sequences. And if I'm not mistaken, all like things like Siri initially were working on this type of neural network. But then another breakthrough came, and transformers appeared. And this is just I would classify them as the next evolution, when instead of having gates inside the neural network that were remembering when to forget and when to remember something, there was a concept of attention. So a neural network kept attention on certain parts of its input at all times. And first of all, it could handle much bigger memory. And second, it was very easily used in parallel processes. You could utilize modern GPUs and parallel processing to very easily train this kind of neural network architecture that was very, very well suited for parallel processes. And this is currently like the big thing. This is what ChatGPT uses, for example. It uses transformers, and GPT-T in GPT means transformer. So yeah, so this is kind of a little bit about recurrent neural networks. But now let's touch the final part, which are large language models. So what is a large language model? It's just a trained deep learning model that understands and generates text in a human-like fashion. And in 2018, before there were just like recursive neural network, long-term short memory neural networks with some supervised trainings, hard to scale. There wasn't anything impressive. But then in 2018, GPT-1 came to power. It used transformers. It used supervised training, unsupervised training, and supervised fine-tuning. It means that the training was done without human intervention, and the training was done on 7,000 books at this time with 120 million parameters. But then humans evaluated the output, and it is called supervised fine-tuning. So the output of a model was viewed and supervised by humans, and that's how we evaluated how good the model was. But then OpenAI, who developed this, asked themselves, why don't we go bigger? And they went bigger, and they created GPT-2, which technically was pretty much the same. Only thing that changed was more parameters, like 10 times more parameters, and much more training data. And it was quite successful. But then why don't we go bigger? And in 2020, there was GPT-3 released, which used the same approach of unsupervised training, supervised fine-tuning, but 10 times again. So it's already 100 times more than the initial. It's 10,000. So it's 100 times more each time. Yes. And again, it's bigger, and bigger. But then in 2020, something happened. And instead of going bigger, they went smarter. And if you look here, the supervised fine-tuning, the process when people were evaluating the results, was changed. It was changed by RLHF, reinforced learning with human feedback. So what was done is they trained another model that was imitating humans who are evaluating the initial large language model. They outsourced the work of fine-tuning and evaluating the model to another model that was trained. And it allowed them to do it on unprecedented scale. Like instead of 100 iterations, they could do 100 million iterations. And that's where it all blew up. And this model then was given a web chat application interface, and that's what we know as ChatGPT. And so this is how we went from the very beginning of humble perceptron to ChatGPT. And since we got there, I have someone who wants to say hi to you. Yeah, and all of those large language models, now there are so many of them. Like you cannot keep track of all of them. There are some you may know, like ChatGPT, Llama, GPT-4, large language model that is evolving now, like Bard from Google. But there are so many, and I don't think anyone in the world knows everything about everything there. So you have to compromise. I just wanted to tell a couple of words in conclusion here. First of all, like AI and neural networks, as any technology, they follow an S-curve when we are looking at development of technology. Technology starts evolving, and then it settles down. And the question is, where are we? Are we at the beginning of this S-curve, or are we at the top of this S-curve? And no one can tell you that. And I think any company that guesses correctly will have tremendous advantage. But at this moment, I don't believe anyone knows this. And lastly, I wanted to close with this statement. Our classical science, like physics or mathematics or chemistry, in those areas, times when a person sitting at his desk with pen and paper could make a significant discovery, those times are long gone. Like now, in order to make any discovery in like physics of particles or in astronomy, you need space telescopes, you need big hadron colliders, you need particle accelerators. Like it's almost unthinkable to think that someone just sitting at home suddenly gets a Nobel Prize or some other discovery, because a lot of things were discovered. But AI, it is at the very beginning now. So the science of neural networks and science for artificial intelligence, this is where a person with a computer or a couple of guys, like a small research facility, they can actually come up with groundbreaking discoveries at their home. And this is fascinating to me. Like this is as if we are back like 200 years when just people were sitting there and making scientific discoveries in other areas. So this is very, very exciting to me, and that's all I had to say today. Thank you very much.
So thanks a lot. This speech was really inspiring and interesting. I see a lot of reactions in the chat, and let's get down to the Q&A part. We have several questions. So the first question is, how do you envision the future of neural networks in the coming years?
I have a very strange feeling towards this. I feel quite optimistic, but I think that they will not be what we think them to be. Think of dot-com bubble, something that was happening not so long ago when internet was just evolving, and when everyone was very excited about the internet, and a lot of overvaluated companies were popping up, and everyone was really psyched about it, and like share prices skyrocketing. But then everything went down and everything collapsed. But it doesn't mean that the internet was useless. It means that it was just different, not what we thought it to be during dot-com bubble. I think something like this could happen in the world of AI. Like currently, there is like this hysteria of everyone trying to get on the train. But probably many of those companies will fail. But those who stay will be in the middle of something beautiful.
Yeah, thank you. So the next question, can you build a 100% valid neural network? If not, then how can you verify if the response is correct, and how can you trust the results?
Of course you cannot. Almost nothing other than mathematics is 100% true. Like in many applications, like 99.9% is as good as 100, especially if we are talking about applications of neural networks, like image recognition. If something is 99.9% true, it's as good, because humans aren't 99.9% true. So neural network doesn't have to be 100% accurate. It just needs to be more accurate than humans in most of the cases.
Thank you. The next question. What about accuracy and performance of text prediction with neural networks compared to other algorithms like Markov model?
Well, this is for researchers to argue about. I don't really know a little bit. I don't know too much about algorithms other than neural networks for text prediction and text analysis. But I think the market shows, like right now, neural networks and large language models are used very widely, and I think it indicates like money follows the most promising areas.
Thank you. So while you are generating new questions, we encourage you to join our community on other social networks like Facebook, Telegram, LinkedIn, and of course, Web community platform via the link in the chat. By the way, don't miss the registration for our upcoming SAP Tech Talk, Smart Start with SAP Build Process Automation. The registration link is available in the meeting chat. So here are some new questions. What are the main updates about ChatGPT 5?
I don't think anyone knows when it's gonna be. It will be massive, of course. Like even updates that we have right now on GPT-4 model are already massive. Like right now they have added vision. So quite recently they added the vision to GPT-4 model, so you can actually feed a picture to GPT and ask it what it is, or you can feed it the screenshot of a website and say, can you generate me HTML to build something like that? So it is already massive, and there are some applications for this. I've heard that this vision for large language models is right now quite used in robotics. So there is it's called RTX, the project where robots are using large language model to perform tasks, because it can now be applied with vision, and robots can kind of orient themselves in the world. Yeah, and GPT-5, I think it will be massive, but there are right now there are competing approaches. GPT-5, which is just going more and more and more, bigger and bigger and bigger. But recently, and this is just to tell you how fast this thing evolves, when I started creating this presentation, I didn't hear about it yet. But by the time I finished this presentation, though, I've heard about this it was called Mistral 7 billion model, I think. It is a model that instead of going bigger, just more parameters, it just works on the algorithm and performs better than GPT-4 in many areas. So maybe big companies will go towards actually smaller models in the future rather than bigger like GPT-5.
Yeah, thank you. So we had two questions about the convolution models and process. So the first one, is this the convolution process or convolution matrix for filtering, meaning the slide number 38. Probably you can open it and check.
Can you repeat the question, please?
Is this the convolution process or convolution matrix for filtering?
I think the convolution matrix that you get is it's not here, it's actually here. It's when you apply all the filters and you get the final result, you get the value at the end at the output of your neural network. And when you compare, like for example here, ideally you would want to have zeros everywhere and 100 near number 7, but you don't. So it means that you you have an error. So that's your matrix, the error of the result versus the expected result. And that's what you're using in your backpropagation to actually change the values of the filter. And I think they also mentioned that 7 doesn't look like 7 too much. Yes, and that's why it's only 0.87% sure. It would be like 99% sure if it was actually looking like perfect 7.
Yeah, thank you. And yeah, actually, your answer to the next question, there is like a comment in the example of convolutional model 7. It looks like 3 for the for Vladimir, if I'm not mistaken. And he asked if it's true, and he asked what about AI here?
Yeah, and in this case, it's kind of sure that it is 7, but it might as well be. But usually when you train this model enough, and you look at the cases when neural network is not very sure, human would not be very sure either. Like that's like there is no magic. It just needs to be better than human in this case.
Yeah, thank you. And one more question. Have you ever used AI as a part of your work and for your project activities?
I would say that like working in SAP, SAP clients are very conservative in AI world, but we have used neural networks for text classification, mostly to do with ticketing systems. When you have a ticketing system and you want to predict the category into which a ticket needs to land, we have used ticket text classification for that, and also a little bit of sentiments, so that the tickets where clients are extremely unhappy would be flagged and kind of reason to attention of humans to deal with the crisis.
Yeah, thank you. And as you see, that's it for today about the. Oh no, we have one more question, so we still have some time. The next question: won't the use of neutral network lead to the fact that there will be a large number of low qualified specialists who got jobs for which they are not suitable for?
Interesting question. I don't think anyone can answer that. I think no. I think that if everyone uses neural networks, everyone will be on the same level. Like also like bad specialists who use neural networks will kind of be a little bit better, but also good specialists who know neural networks will be much, much better. So everyone will be able to use them. So everyone will be on the same, like there will be no advantage or disadvantage to anyone. Maybe in the beginning when like not everyone wants to use them, not everyone is aware that they exist, it could happen, but eventually the technology will catch up. And if even a weak programmer can become an average programmer by using like Git Copilot, imagine what a good programmer can become.
Yeah, thank you. So yeah, I think that's it for today. I would like to thank you very much for an interesting speech, and there are a lot of compliments on your tech talk in the chat. You can then watch all of them and read. So as already mentioned, our today's webinar recording will be posted on our YouTube channel. The links to the recording will be sent separately. Colleagues, thank you very much again for your participation, and have a nice day.
Thank you very much. It was a pleasure. Bye-bye.